Welcome to part 2 of Monday, March 8th, AP Chemistry here at St. Park High School. Once again, if you're enjoying these exciting chemistry videos, please feel free to subscribe to my channel. I'm up to 80, going for 100. Come on, come on. All right, so this is dealing with acid-base character and chemical structure. So explain the following observations. HNO3 is stronger than HNO2. Who wants to take a crack at that one? Go ahead.
It has more oxygens.
Okay, so that's true, but we have to explain that what does that do?
It's more electronegative. It takes away like the electrons from H.
Okay, HNO3 has an extra oxygen, which is an electron withdrawing group. What does that do to the H? Makes it more positive or more polar, okay? Or really, which makes it more, and the key word we would put is ionizable, okay? So since HNO3 has an additional oxygen, the oxygen is a strong electron withdrawing group, makes the hydrogen more polar, thus more ionizable, and it's a stronger acid. So it's not a one phrase answer, it's a full sentence to 2 sentence answer. Okay? Some of you gentlemen like to do phrase answers, not sentence complete answers. We need sentence complete answers when we do these. Okay, so somebody else. H2S is a stronger acid than H2O. Okay? H2S is bigger, so what does that mean? The bonds between the sulfur and the hydrogen are weaker. Okay, and you just kind of have to look up in the periodic table and see how the two are arranged to each other. Okay? So because sulfur is larger than oxygen, the bond length between the sulfur and the hydrogen is longer, thus weaker, so the hydrogen is more ionizable in H2S than it is H2O. And whenever you're given a comparison, you always have to speak about both parts. You don't just say one and assume that that means everything opposite of the other. Okay? You have to assume that the readers are very ignorant. Okay? Because they don't know you. You have to prove to them that you really know what you're talking about. All right, now we didn't really talk about this one. H2SO4 is stronger acid than HSO4. When we have 2 hydrogens, this is called a diprotic acid. It's got 2 protons, a diprotic acid. When molecules lose hydrogens that are diprotic, they lose one at a time. So it's going to go from H2SO4 to HSO4. All of them will do that. Then once they're all lost one, then they'll begin losing the second one. Now, why do you think this one would be much more hesitant to lose the hydrogen than this one? No? What charge is the H plus? What charge is my ion now? So now you're trying to take something positive away from something that's now negative. It's always harder to remove successive electrons. It's always harder to remove successive electrons. So if we look at up here on this chart, H3PO4 has a Ka of 7.5 times 10 to the minus 3. A relatively strong weak acid. But then you come up to the top right where you have H2PO4, a third on the right column, third way up, H2PO4, losing one more hydrogen. Notice now it went to 6.23 times 10 to the minus 8, much less product favored. Then you come all the way down here to HPO4, losing the second, probably now the third hydrogen, and it's 2.2 times 10 to the minus 13. It's always harder to remove successive electrons because you're taking something positive away from something that's becoming more and more negative. Okay? So when you have di and triprotic acids, the second hydrogen is always harder to remove than the first. Now with H2SO4, since it's a strong acid, we do make a false assumption that both hydrogens get donated and that this would be a diprotic. So if I put in 0.1 molar of this, then I would assume that my H plus is 0.2 molar. But the reality is it's going to be something less than that because this doesn't ionize 100% in reality. But most of the time when H2SO4 is given, it's assumed that it's going to ionize 100%. All right. H2SO4 is a stronger acid than H2SeO4. Who wants to take a crack at that one? Who's already answered several?
Sulfur is more electronegative than sodium.
So that makes it more, makes the hydrogen more polar, but what do we call the, well, the hydrogen becomes more ionizable, but I'm looking for the phrase before that. What does the electronegativity have to do with anything? Because it's what? Two-word phrase. More electron withdrawing. Okay? The more electronegative element is more electron withdrawing, which causes the hydrogen to be more polar and thus more ionizable, making this a stronger acid than that. Okay? What am I missing on E? Isn't it the same thing? I think this is, it should be just like a CH2Cl, just one chlorine on this one and 3 chlorines on that one. Let's just say it was that. Okay? If it's 1 chlorine here with 2 more hydrogens versus 3 chlorines, which one's going to be the stronger one? The one with 3 chlorines, because they're highly electronegative and more electron withdrawing, making this hydrogen more polar, thus more ionizable, causing this to be a stronger acid than that. Now, let's look at these exact same two, but let's put a carbon. They're both CCl3, but let's put a carbon in between here. Put another carbon there. So there'll be 3 carbons in this chain with the chlorines on the end terminal carbon. Now which one's going to be stronger? First one, because even though we have the same number of electron withdrawing groups, this is farther away and have less of an effect. And therefore, that would make that hydrogen more ionizable. Okay? So we have binary acids, we have oxyacids. We need to be able to identify the strengths of those based upon the oxygens, the hydrogens, and really the structure of the molecules. So, just take a second in your notes. You see what you can do on 88. Practice writing complete sentences, not phrases. 88. Let's stay focused here. just for the last one, there's structures of benzoic acid and phenol. The first one was the last.
The last.
So how did the Kool-Aid? The Kool-Aid? If anybody wants to buy me an Android phone or have an old Android phone, they want to give it to me. Make it a much easier way to video, because I can pause it. I can buy video without it being hooked up to any kind of service, couldn't I use an Android phone just as a video without it being hooked up to any kind of service? And then I could just plug it in, hardwire it into the computer and upload. It'd probably upload better and easier than the iPhone videos, which don't upload to YouTube at all directly.
Also, I think don't have MLB format, which isn't the best, because YouTube is expecting an MP4 form.
So is Android doing that?
Yeah.
Yeah. So if you have an old Android phone sitting around that has decent video, you can donate it to the school. We'll use it. It'll make, that way I won't have these long pauses in the videos.
I'll look around.
All right, how many would bet me a nickel that you were able to answer all of these correctly? Felt good, bad, ugly about them? I mean, most of them? All right, so why is HCl a stronger acid than H2S? I actually had used that as an example earlier. Nathan, what you put?
HCl is stronger than H2S because Cl is more electronegative in comparison to
Okay, which causes the hydrogen to be
uh,
more polar. thus more ionizable. Okay? Than the H2S, so it's a stronger acid. Okay, so that's the one. Now again, sulfur and chlorine are right next to one another. So size isn't going to be a big issue. They're about the, chlorine's a little bit smaller, but just a tad smaller. The electronegativity in that sense then is a greater influence. So, but again, we want to look at the electronegativity of a binary acid secondary. The only time you're going to use that is when they're about the same size. Now, H3PO4 is stronger than H3ASO4. Anna, what you get on that one?
The phosphorus is more electronegative than the AS, and so it has a stronger affinity for the electrons, so that H plus becomes more polar and therefore more ionizable.
Okay, good. So, and another way, she said a greater affinity for, which is fine. You could say it's more electron withdrawing. Okay, that's my kind of catchphrase, is electron withdrawing. But a stronger affinity for electrons is the exact same thing, so that's 100% correct. Okay? Advice, what you get for HBr3 is stronger than HBr2.
The extra oxygen in HBr3 makes it more electron withdrawing than O2 in HBr2, so that makes the hydrogen more polar, more ionizable.
And a stronger acid. Perfect. Perfect answer. Okay? Now HC2H4, what would be the name of this one? Does anybody remember C2O4? Look up here. What's the name of C2O4 ion? Very bottom of the third column. Oxalate. So what's the name of this acid going to be? Oxalic acid. 8 goes to ic. Okay? Oxalic acid versus the hydrogen oxalate ion, or the binoxalate. They put an N in there for some reason. I guess bioxalate, they say binoxalate. Okay? What's the simple answer on that one, Ben?
HC2O4 minus has a negative charge, so it's harder to remove successive electrons.
Well, there you go. It's hard to remove it. It's something positive from something that's now negative. And then lastly, benzoic acid versus phenol. So here are the structures. What does the circle inside this cuculae, I don't know how to put the accent on the last E here. What does the circle mean?
The double bond resonate.
Resonance. Okay? Remember, these double bonds could just as easily be in alternate positions. Okay? And so we have resonance. So this is actually AX3 on each of the carbons. Anybody remember the shape of AX3?
Planar.
Trigonal planar. Okay? And by the way, that's another one of those memorizable things that's coming up in April. So we don't want to forget that. So, but it's planar. So all these are AX3s. They're all trigonal planar. So this is a flat hexagon that each has a non-hybridized p orbital perpendicular. Each carbon does. So there's 6 p orbitals in that hexagon on perpendicular to the plane. Those all overlap one another and totally delocalize the electrons. So you get this cloud of electrons above and cloud of electrons below that benzene ring. Very stable. Okay? So that's what that means. So again, this is the exact same thing as that. Just a lot easier to draw. Okay? Since organic compounds get complex, they figured out shortcut ways to draw it. So I just want you to just always know there's at each vertex is the carbon. Then you always assume there's enough hydrogens to fill the valences to give carbon 4 bonds. Okay? So, is this going to be an acid? No. It's just really like an alcohol. Anytime a carbon is attached to an OH is attached to a carbon, it's going to act like an alcohol. That's what the OL part of phenol means, that it's an alcohol. There's not enough, it's not polar enough to make that hydrogen ionizable. But why would this one be? Because of that second oxygen makes it more electron withdrawing, makes that hydrogen more polar, more ionizable. Okay, it's the presence of the second oxygen that makes the whole thing more electron withdrawing, causing the hydrogen to be more ionized. Okay, so OHs are not going to be acidic or basic. This bond, all these bonds are too strong, they're not going to break in water. Now you would have hydrogen bonds, it would make it soluble in water, but it's not going to break apart in any way, ionize any way in water. Is everybody comfortable with being able to identify the strengths and be able to say the Y's? 100% guaranteed that will be short answer question on my test. Okay? So if you need to put an asterisk, star, whatever, will be on the test. Kind of very similar to this. And we know all of learning is all about just, hey, what's on the test, right? That's the all motivating force for all learning. It shouldn't be, that's exactly right. It should be our intrinsic desire for knowledge, which will hit you at some point around 30. Once I got out of college and I was teaching for a while, I started tutoring organic chemistry, which organic chemistry is just, you just fight through. I mean, there's just so much memorization in organic chemistry. But then I started tutoring it, and I was kind of go back and having to kind of relearn some of the stuff because it's been a while and all that. I said, wow, this stuff's really interesting. Now that I don't have to know it, and I get to know it, it really kind of, it's kind of fun. So once it's out of the you have to do something mode, and you learn stuff of what you're interested in. But this is teaching you how to learn. Okay, so you got to do this before you get to that. But hopefully you want to be a lifelong learner. Okay, let's talk then now about real acid-basic equilibrium. Ooh, I get to erase all this. Do you guys know what I mean when I say wax on, wax off?
Yeah.
You all seen Karate Kid? The original one with Mr. Miyagi?
Really? You can't serious. What are you doing?
I think we should watch
We
it
gotta
on
watch
Wednesday.
it.
Yeah, watching class.
The second one, the sequel, I don't know, it's when they're adults and it's the kids kind of, that one's kind of goofy.
We need to watch it on Wednesday, so Abba can be cultured.
Oh, you're right, I do.
Anyway, the reason I say that is because when I do this board, I always feel wax on, wax off.
Was it really good or was it weird?
Weird.
Kind of sucked. The new forensic, like the only reason that.
All right. All right, so now we're going to talk about just weak acids. Strong acids, they ionize 100%. We can calculate the pH. We can now identify the strengths, which one makes them stronger or weaker. But what we really want to know is how do we find really the pH of a weak acid given the Ka, or how do I find the Ka given the pH? Okay? So we'll start with how to find pH of a weak acid given Ka. What do you think the A stands for in Ka?
Acid.
The acid constant, okay? So K is K, products over reactants, coefficients raised to powers, okay? We had Kc, Keq, Kp, that's just generic equilibrium. Now we're specifying a specific type of equilibrium, acids and bases. So we're just gonna change the subscript to Ka and to Kb. Kw meaning that the equilibrium constant for water. So the subscript just kind of describes the different types of reactions. It doesn't change how we calculate K at all. First things first. All right, so the most common weak acid is acetic acid. Put that into water, and we're going to get CH3 COO minus plus H3O plus. Now, notice that water is a liquid, so what does that mean in terms of the equilibrium? It's not there, so sometimes they'll write this without the water and just make this H plus out here rather than H3O plus. 6 to one hand, half a dozen to the other. Okay, however you want to do it. Now, let's talk in terms of Arrhenius definition. Why is this an acid?
The H plus concentration increases.
Because we made H3O plus. In terms of Bronsted-Lowry, somebody else, what in terms of Bronsted-Lowry, why is this an acid?
Proton donor.
It's a proton donor. It's donating the proton to the water. According to the Lewis definition,
Electron accepted.
the H plus here is accepting the lone pair of electrons on the oxygen. So the oxygen's donating the pair of electrons. The H plus, this is the source of the H plus that's accepting it. So it's an acid by all three definitions. Now, let's just say, though, that I put in our 0.1 molar of this initially. And we have 0 and 0. But now, because it's a weak acid, can I assume 100%? No. So this is where I have to use equilibrium. So I have my Ka is given as 1.8 times 10 to the minus 5. That's given Ka. So my equilibrium expression, 1.8 times, well, let's finish my ice table first. So what's the change going to be? Minus x plus x plus x. So 1.8 times 10 to the minus 5 is going to equal CH3 COO minus H3O plus CH3 COOH. So now we just plug, right? X times x times 0.10 minus x. Now that's kind of complicated, but what do you think we get to do?
Put in the calculator.
No? Easier.
It's negatively equal.
What is?
The,
X in the denominator.
yeah.
Because this number is so small, the amount that's actually going to ionize, the x, the minus x, is going to be so small that 0.1 minus x is still going to prefer 2 to 3 sig figs still equal 0.1. So we assume the x is negligible.
That's not a point.
Therefore, 0.1 minus x still approximately equals 0.1. So now it's easy. So now we end up with x, which is equal to my H3O plus, is equal to the square root of 0.1 times 1.8 times 10 to the minus 5. And that's actually, you can go straight to this, that we're going to do this so many times that we're going to find that you set this up, you go straight to here. I mean, especially on a multiple choice question, you just, it's the square root. So this is going to be 10 to the minus, so it's going to be 1.8 times 10 to the minus 6. We take the square root of it, and someone's getting me that value.
.3 times 10 to the negative 3.
Okay, so notice it's 1.3 times 10 to the minus 3, so if we had done 0.1 minus that, we would have gotten, 0.8987, I think. If I subtracted that, maybe even 0.9987. Still, to 2 sig figs, it's gonna be 0.10. The rule is that this number has to be at least 1,000 times smaller than that. Okay, as long as there's 10 to the third difference between these two, you can make that assumption. Now, the bigger the difference is, this goes to -7, -10, -12, the better the assumption is. Okay, because the x becomes less and less and less significant. So how do I find the pH of this? So the pH is equal to the negative log 1.3 times 10 to the minus third. And that equals 2.87. So notice that HCl 0.1, the pH was 1. This one is 2.87. So it's almost 100 times weaker than HCl, because we're almost at 3. All right, so calculating given the Ka, it's always just going to come down to the initial concentration times the Ka square root is what H3O plus is always going to be. So we plug that in, so what is the pH of, pick one, HF? Well, it's too strong. We'll do benzoic acid of a 0.25 molar C6H5COOH solution. Ka is equal to 6.5 times 10 to the minus 5. Okay, so you do that one. Write out the equilibrium expression. Actually, let's do three things. Number one, write the equation for the ionization of C6H5COOH in water. Write the equilibrium expression and then 3 pH. on, Grace, what's the equation gonna be?
C6H5CO minus plus 3. It doesn't matter.
Okay, so notice she didn't include the water, but that's 100% fine. Okay, it's sometimes a lot easier just to write it without the water. Okay, so the equilibrium expression, Anastasia, what's the equilibrium expression gonna be?
So do you want me to add in the 6.5 times 10 to the negative?
We can include that since we know it.
Do you want me to put in the numbers or just like the
No,
actual?
the actual expression. The expression, when it's asked for this, they don't want numbers.
Okay, so C6H5CO minus, and then the H plus, and under it is the H5COOH.
Okay, so that's my equilibrium expression. So I'm putting in now initial 0.25 molar, 0 and 0. So I know that this is going to be plus X, and minus X. Okay, so now I just can say that the H3O plus is going to equal the square root of 0.25 times 6.5 times 10 to the minus 5. And that equals,
2.40.
that's the pH, right?
Yeah, 4.0 times 10 to the minus 3.
4.8
No, 0.
4.0.
times 10 to the minus
3.
third. So then the pH is equal to the negative log 4.0 times 10 to the minus third, 2.4.
2.40.
Now there is a rule for Sig Figs with logarithms to where I just can't remember. I think when it's this, when you have two Sig Figs here, you go to two, and you take the log of it. There's two decimal places, and then when you're going the other direction, 2 decimal places would tell me that if I'm going taking the inverse log, I'm going to have 2 Sig Figs. I think. I'm never going to hold you to that, but I think that's what the rule is. All right, 5 minutes. Got time for one more. Let's go the opposite direction. Looking at question number 51. Lactic acid, that's what builds up in your muscles when you exercise. Lactic acid has one acidic hydrogen, it's monoprotic. Notice all those hydrogens in there. Which hydrogen do you think is the one that's going to be ionizable? This one on the very end, that your COOH, you have to recognize that that's your carboxylic acid. Okay? So, I don't feel like writing all that out. So I'm just going to say HX. Okay? It's going to go to H plus and X minus. The X minus is all of this. Okay? It's just, but in my equilibrium, that's not really going to affect anything. I don't need, I just, now on a test you need to write it out, but for just doing it, we don't have to. We have a 0.1 molar solution. Okay? But this time it says it has a pH of 2.44. Calculate Ka. So what does the pH tell me? If I'm given the pH, what is that really telling me? The concentration of my H plus, right? Because I can say that 2.44 is equal to the negative log of H plus. So I then go 10 to the negative 2.44 is equal to H plus. So somebody H plus is equal to 3.63 times 10 to the minus 3. Okay? So now I know what H plus is. So if H plus is this must have been plus 3.63 times 10 to the minus third. So at equilibrium, I have 3.63 times 10 to the minus third of this. The same thing here. And this is going to be 0.1 minus. Now there's no need to make an assumption now. Go ahead and subtract. This is going to be minus 3.63 times 10 to the minus third. So K is going to equal 3.63 times 10 to the minus third squared over, what does that come out to? Anyone?
0.104.
It can't go up. You gotta subtract it.
Oh, I got it.
So it's gonna be 0.996. 0.0996. Do I?
0.096.
Yeah. Okay? So that's my equilibrium, so now I just plug that in, so somebody give me a final answer and we're done. Times 10 to the minus 4. Okay? So, if you're given the pH, you're really given the H plus. We'll do a few more of these on Wednesday. Tomorrow, you're just going to have the little reading excerpt. Okay? Have a great day.